Great. So what's really nice is that we're small crowd, which means we can have a lot of in-depth conversation, which I feel like we've not been able to do so far. I have to introduce Amory, and I will just say one thing, which was my favorite introduction of him, but I found out his favorite introduction of himself too, which is the MacArthur Genius Award winner. So that's, you don't get to say that so often, so thank you. And Amory, it's up to you how you want to organize the format. But I think as much discussion after your presentation would be great, yeah?
We'll get to that.
Great.
Okay, and I'll actually start with a little amuse-bouche of the past half-century's gyrations in the world oil market. For any economists who might be here. Are there any economists in the house? No? Oh, well, that's good. But the past, this is characteristic of most commodities, but of course exacerbated by oil's strategic importance and unstable geopolitics. So from 1970 to 2019, world demand for oil grew gradually but remarkably steadily despite wildly fluctuating prices. But instead, here I'm graphing price against demand, and that reveals, starting at the lower left, this wild roller coaster ride with repeated loop-the-loops, just as other commodities do. That is, when price rises enough, demand falls, then price crashes, then the cycle repeats. Yeehaw, fasten your seatbelts. But of course, meanwhile, oil's become uncompetitive, as I explained in the previous talk, even at low prices. And so far, the oil savings have come from incremental technologies moving at the pace of big, slow industries in old, stodgy markets. But what if innovations as stunningly fast and game-changing as LEDs in lighting move demand dramatically back down towards the left? Well, maybe we're about to find out. So by way of explaining how, I'd like to remind you about how to design whole systems for radical energy efficiency or other resource efficiency, thus protecting climate, not at a cost but at a profit. And this practice applies orthodox engineering principles, but it asks different design questions in a different order to get different answers. I teach this material 2 terms a year at Stanford, and I hope soon to post my lectures free online. A little history. Around 1975, U.S. government and industry all said that the primary energy needed to make $1 of real GDP could never drop. A year later, I heretically suggested it could drop 72% in the next 50 years. So far, it's dropped 61% in 46 years, with 28 times the cumulative effect of all the renewable growth. And yet, just the efficiency innovations already added by 2010 can save another threefold, twice what I originally thought, at a third the real cost. And today, even that is looking conservative, because optimizing buildings, vehicles, equipment, processes, factories, as whole systems, not as piles of isolated parts, and for multiple benefits, not single benefits, could often make very big energy savings cost less than small or no savings, turning diminishing returns into increasing returns. Economic geologists know that the reserves of a mineral, the economically extractable deposits that are at current technology and price, are only a small part of the whole resource base, but can expand with innovation. And similarly, reserves of conventional energy efficiency, like the bright green zone in these mineral resource definitions, are several-fold smaller than the full efficiency resource exploitable by integrative design. And that's set out in this peer-reviewed paper and 2 more after, explaining why making energy saving several-fold bigger can actually cost less, because it uses not more but fewer devices, not fancier but simpler devices. It doesn't add stuff, it takes stuff out, but the devices are more artfully chosen, combined, timed, and sequenced. The 4 arts built into integrative design. We're used to resources like copper ore bodies and oil reservoirs that are finite and depletable assemblages of atoms. But energy efficiency resources are instead infinitely expandable assemblages of ideas whose use depletes only stupidity, a very abundant resource, maybe an increasing resource. So how do we do this magic? Well, one of my early mentors, the inventor Edwin Land, said, don't undertake a project unless it's manifestly important and nearly impossible. He also said, people who seem to have had a new idea have often just stopped having an old idea. That's the hard part. And Asian tradition similarly urges us to seek original mind, beginner's mind, child mind, opening ourselves to new ideas by shedding all assumptions and preconceptions. And that is the first and hardest step in the method of integrative design. So in that spirit, Caltech's late great aerodynamicist Paul McCready reminded us that decades of textbooks on creative thinking have posed this problem as find the solution that connects these 9 dots with just 4 lines without lifting your pen from the paper. So you're supposed to, let's see, how does this turn on? Yes, so you're supposed to think 1, 2, 3, 4, oops, 5, that didn't work. Let's try diagonally, 1, 2, that isn't going to work. And of course, what you're supposed to do is think outside the box, which is where that expression comes from. But one day, a student startled her professor by saying she'd solved this problem with just 3 lines. Oh, 4 was hard enough. How do you do 3? Dots are infinitely small. Well, actually, these are rather plump dots, and you don't actually have to go through the middle of them. So if your paper's wide enough, you can do this trick. And then the students started to feel liberated, and you know what happens then. They started to solve this problem with 1 line. I'll get you started with a few of the nice 1-line solutions. If you're Japanese, you might think of the origami method. If you're a geographer, you might want to use a very long line. If you're a mechanical engineer, a tool-using creature, you could, of course, use a tool called a scissors to cut out the dots and impale them. There was no rule against that. If you're a statistician, you might want to crumple up the paper, and if you keep stabbing it over and over with the pencil enough times, eventually you'll go through all 9 dots at the same instant. And the one I like best came from a 9-year-old girl who said, you didn't say it had to be a thin line, so I used a really thick line. So, as Paul McCready said, this tyranny of the word the, find the solution with 4 lines, put us back in the box and kept us from being more creative in finding more elegantly frugal solutions. So with beginner's mind, never having built a house before, hence not knowing what was impossible, in 1982 I did the conceptual and energy design of the owner-builder house where my wife Judy and I live near Aspen at 2,200 meters elevation, where the outdoor temperatures used to dip to minus 44 Celsius with up to 39 days of continuous midwinter cloud. But our house does no combustion. That's so 20th century. Super insulation, ventilation, heat recovery, and super windows that insulate like 16 to 22 sheets of glass, but look like 2 and cost less than 3, make this house 99% passive solar heated, 1% active solar. And if efficiency added less construction cost than eliminating the heating system subtracted, so it got cheaper. And then saving also 90% of the electricity and 99% of the water heating and half the water, all the savings paid back in 10 months. With 1983 technology, today you can do a lot better. Now the central atrium, seen here in a February snowstorm, has so far produced 80 passive solar banana crops, along with a bunch of other tropical fruits. There's over 100 kinds of higher plants in there. And without needing to look like this, our house helped inspire several 100,000 European passive buildings and was even put into an analogous design adapted to Bangkok. And almost everyone on Earth lives in a climate somewhere between Bangkok's and mine. Integrative design gives you lots of benefits for each expenditure. So at the top of the upper middle photo, the white arch holding up the middle of the building has 12 different functions, but it has only one cost. Now, We start then with the end-use effect that we want, and to deliver it, we optimize buildings as whole systems, not as a bunch of components. We pay for the efficiency by shrinking the needed supply, and maximize those capital savings by applying efficiency in the right order from downstream to upstream, as I'll elaborate shortly. And then we should reward the design professionals for what they save, not what they spend, and optimize the sequence and timing of design steps. So some other examples of how that works. Most lighting retrofitters start by installing higher efficacy source, more lux per watt, and better controls. But the Illuminating Engineering Society's Handbook of Fundamentals actually and rightly tells us first to improve the visual quality of the task, like clean the photocopier optics, then improve the geometry and the cavity reflectance of the space, how it bounces light around, and the quality of the light, cutting the veiling reflections, like from direct downlight bouncing off the paper into your eye, and killing the contrast between the ink and the paper. That's what lets you read. If instead of lighting volume, you light surfaces, lighting up and on the walls, then the rays come from every which angle, and hardly any of them will be at a bad angle. So you can see about 7 times better with the same light, or as well with a seventh the light in a typical office. And then you should harvest or optimize the amount of light, and harvest and distribute natural light, and only then optimize the luminaires, the fixtures, and the controls and maintenance and training. Now, this sequence can often save an order of magnitude more energy and look better and look nicer, but the fixture count and the capital cost go down, not up. And most lighting retrofitters do this in reverse order, worst buys first, so they don't get the benefits. Or to keep people comfortable in hot places, first cool the people, not the building, which has no comfort sensation. Decades ago, I asked my hostess in Japan in a sort of paper house, why don't you heat your house? And she said very sensibly, why should I? Is the house cold? So in these hyper chairs at RMI's office in Basalt, you stay comfortable in air temperatures from about 16 or 18 up to about 30 degrees, using 3.6 watts of silent fans in the summer and 14 watts of electric car seat heater in the winter, all run off a little lithium battery pack. Then you expand the range of conditions in which people feel comfortable. For example, good ceiling fans can expand the summer comfort range by 5 to 7 Celsius. Then you minimize unwanted heat or humidity gains within or into the space. Then you apply passive cooling, then active but non-refrigerative cooling. Next would come super efficient refrigerative cooling, like Liang Lok's tripled efficiency but cheaper HVAC in Singapore. And now we can actually do upwards of COP8. And next, if needed, would come cool storage and controls, but actually we need never get that far down the list as refrigerative cooling to save 90 to 100% of the cooling energy with better comfort, better uptime, lower whole system capital cost, even in the most severe climates. Most practitioners, again, do these things in reverse order, worst buys first. So the sequence really matters. And these methods are improving. Our integrative design to retrofit the Empire State Building saved 38%, later 43% of its energy with a 3-year payback. I'll show you how in a minute. 3 years later, our cost-effective Denver retrofit of a big federal complex saved 70%, making this difficult half-century-old building more efficient than what was then the best new U.S. office, which in turn is only a third as efficient as RMI's all passive, net positive, no mechanicals office near my house. And then there's this Bavarian building using 2/5 less energy than ours. And yet all these technologies existed a decade ago. What mainly improved is not so much technology as design, how we put the bits together. As in the Empire State Building, where we first set up a window factory on a vacant floor to remanufacture all 6,514 units from double glazing into super windows that pass light through but block heat. And that plus better lights and office equipment and so on cut the maximum cooling load by a third. But then renovating smaller chillers instead of adding bigger chillers saved over $17 million of capital cost, paying for most of the other improvements and cutting the payback to 3 years, or less than 1 year had we counted the non-energy benefits to the owner or the tenants. By the way, a major energy service company also bid on this job. They offered a 3-year payback with savings 6 times smaller than we got, so they didn't get the work, fortunately. They just had disintegrated design. Similarly, in 6 muggy Indian cities, 1.5 million square meters of integratively designed offices are using about 80% less energy than the Indian norm, with 10 or 20% lower construction cost, but superior comfort and satisfaction. Glare-free lighting, as you see in the big floor plate on the right, is delivered throughout by contract. If workers complain of glare and demand blinds, then the architect doesn't get paid. Now you've seen this graph already, and of course I prefer data to theory, so I do not fit a rising cost curve to the scatter. I just point out that the reason some of the costs are high is they were badly designed or badly executed, make them like the ones on the bottom. Now, timing matters as well. When you're retrofitting a big glass office tower, you can use super windows tuned to each elevation, each side, plus efficient lights and equipment and daylighting to shrink the mechanical loads and systems by a factor 4, and that more than pays up front for the efficiencies that shrank the mechanicals, just like in our house. Now, a 4-fold efficiency gain in this old Chicago office tower at the rear there could thus pay back in about -5 months. In other words, it's cheaper than the routine 20-year renovation you have to do anyway because of failed glazing seals, and that saves nothing. But to make it cheaper, you have to coordinate that deep retrofit with the routine renewal of the curtain wall or some other major building event like renovating the mechanicals or perhaps a financial event, rolling the leases or doing a refinancing or whatever. And it's going to take decades anyhow to do deep retrofits of all our big buildings, so let's right-time them to make the savings much bigger and cheaper. And that's why at retrofitdepot.org we've got software to figure out how to right-time the retrofit across a whole real estate portfolio. Now, how about the kit inside the buildings? Well, in Switzerland, this fist-size heat pump can deliver about 6 to 15 units of hot water per unit of electricity. And this dramatically more efficient, safe, and otherwise superior Swiss cooking system uses vacuum-insulated pots and other innovations. Also, there's a teppanyaki option. To be 2.5 to 4 odd times more efficient than induction cooking. So both of these are several-fold more efficient than market norms and could make it a lot easier to convert buildings from gas to all electric. Now in industry, which uses half the world's energy and electricity, similar methods apply. Paul Westbrook, for example, and I co-led the redesign of this Texas Instruments wafer fab to use 40% less energy, but with 30% or $230 million lower construction cost. So it got built in Texas, not China. And the system efficiencies eliminated one of the 2 utility floors. And by 2017, this had inspired cutting the company-wide chip-making energy intensity by 62%, water 56, greenhouse gases 57. RMI's next wafer fab design after this showed how to save about 2/3 of the energy use and half the capital cost while eliminating all 22,000 tons of electric chillers with any of 3 natural cooling methods that can each give you over 100 units of cooling per unit of electricity. Now, you've seen what can be done in industry on retrofit or new build, I'm going to repeat a few slides here from my earlier provocation, but they may make more sense the second time. And in particular, the better pipe and duct design it just takes two changes in the design process. First, we specify big pipes and small pumps, not small pipes and big pumps. You see, the friction in a pipe falls as nearly the fifth power of its diameter. So how fat should the pipe be to optimize the friction? Well, the textbooks say to make the pipe just as fat as will repay its extra cost over the years from the saved pumping energy. But that's wrong, even though it's in all the textbooks. It's wrong because it leaves out the capital cost of the pumping equipment. A pumping system's pump, motor, inverters, electricals must all be big enough to overcome the friction. So their size and roughly their capex will fall as nearly the fifth power pipe diameter, yet the capital cost of the fatter pipe rises as only about the second power of diameter. So when we optimize the pipe as a component, we're pessimizing the system. Instead, if you optimize the whole system at once, you get fat pipes and tiny little pumping equipment, so the total capital cost goes down. Now, the second shift in design is even simpler and therefore harder. That's to lay out the pipes first, then the equipment, not the other way around. You know, traditionally you put the tanks, boilers, and so on in convenient or arbitrary or traditional places, and then call in the pipe fitter and say, please connect point A to point B. But by then, A and B are far apart. Other stuff got in between them. They're at the wrong height. They face the wrong direction. And by the time the pipe snakes its way across the space, all dressed in neat right angles like they teach us in trade school, it has about 3 to 6 times the friction it would have had with a straight shot. Now, the pipe fitters actually like this because you pay them by the hour. They mark up the extra pipes and fittings, and they're not paying for your bigger pumping system or your bigger electric bill forever. But for you as owner, it's smarter to make pipes fat, short, and straight than skinny, long, and crooked. Thus, low-friction pipes make the blue pump so tiny it looks like a decimal point error. And you noticed we raised it up on a plinth to meet the pipe rather than traditionally dropping the pipe down to the pump on the floor and then back up again with lots of right-angle bends. And the 10 chillers here, normally in a neat row, are staggered to eliminate the pipe elbows. And yet such rearrangement of designers' metal furniture remains largely unnoticed and unpracticed. Again, because it's not a technology, it's a design method, but all our taxonomies of what we should do and the policies to drive them are about technology, not design. In fact, probably no climate model even competes or compares efficiency with supply. And that flaw, 1 of 10, can exaggerate energy needs even more than leaving out most of the efficiency resource. Now, tenfold energy savings, say, in pumping might seem incredible, and yet your heart at this moment is pumping blood about 10 times as efficiently as in traditional industrial piping systems. If your body's roughly 100,000 kilometers of fractal blood vessels, down to the little tiny ones, had the design and friction of standard industrial piping, you would need a heart bigger than your body, very inconvenient. But in fact, your 1/3 of a kilogram, 1.5 watt heart suffices because your blood follows nature's standard design, which is called laminar vortex flow. That's a whole other conversation about the other big design revolution, biomimicry, or innovation inspired by nature, like the nose of the Shinkansen trains that is inspired by the beak of a kingfisher bird. You know, they can dive into water at high speed and, like a 800-fold or something density difference and not get a concussion, and it gets its fish. Now, without biomimicry, back to the pipes again, in this California museum, our wonderful colleague Peter Rumsey retrofitted an efficient piping layout that cut the pumping energy by 3/4 with a 2 or 3 month payback and eliminated 15 pumps that will never again waste energy and maintenance costs. You notice the Y joint instead of right angle bends, a sweet bend and then a diagonal through the air, fat pipes, no right angles. Then he repiped another pumping loop and added variable frequency drives, and together those doubled the flow and saved 85% of the energy. Peter simply asked the pipe fitters to lay out the supply pipes as if they were drains, because in another part of their brain, they know that if drains have a right angle bend, they're only driven by gravity and they'll clog. He just tried to apply it in a different way. And here's how most buildings pipe cooling tower water back to the condenser. But if we lay it out instead the way Peter does, everything gets better. The only obstacle is force of habit. That's why we need to bend minds, not pipes. Now, what do such savings mean for the pumps and fans that use half the torque of the motors that use over half the world's electricity? Well, from the fuel burnt in the thermal power plant to the flow out the pipe, the end use, so many successive losses compound that only 1/10 of the fuel energy comes out the pipe as flow. That means that if you now turn those compounding losses round backwards from right to left, they become compounding savings, and every unit of flow or friction you save in the pipe saves 10 units of fuel cost, emissions, and global weirding back at the power plant. I haven't yet found an engineering text that points this out. They all behave as if, successive losses are multiplicative and multiplication is a transitive operation, so the sequence doesn't matter. It bloody well does matter for the reason I've described. And also, as you go back upstream, the components get smaller and cheaper, reducing the total capex. So always start your savings downstream. Start at the end. Start with intent, with purpose, and then your design logic flows back upstream in the opposite direction to the energy flow. Now, let's apply this logic to big old data centers. 2/3 of the fuel fed into the thermal power plant is lost in the plant and in the grid, and then half the metered electricity is lost in the cooling system and the uninterruptible power supplies, which are together half the capital cost of the data center. And that's before the energy gets to the servers. Then half the server energy doesn't get to the chips because it's lost in inefficient, usually very underloaded power supplies and in lots of fans to take heat that largely shouldn't be there off the motherboard into the room so we could do dumb things with it. Then the next problem is severe underutilization of computing resources, partly through insufficient virtualization. That is, we have one physical server per application rather than putting a lot of different kinds of software onto the same server and turning off the zombie servers. So the resulting energy flow, a little yellow thing way at the lower right, is about to vanish, so let's magnify it before it goes away. Next comes bloatware, running many unnecessary threads and processes and making simple tasks very complex because compute cycles were cheaper than programmers' attention and someone else was buying the energy. Downstream of all that, you might even have inefficient business processes. And if you multiply the red numbers across, or take ratios of the red numbers across the bottom, you can see that only a few 100,000ths of the original fuel energy is actually delivering customer value. Where should we start fixing this? Downstream, okay? So first write elegantly terse code, optimally compiled, with the goal that every compute cycle is a needed and wanted one. I had assumed when we made this diagram in 2009 that this could save an order of magnitude in compute cycles. There are recent tests suggesting it's 2 orders of magnitude. And now the shift to mobile devices makes this sort of saving very valuable because efficient code stretches battery life. Okay, next you can at least quadruple the server efficiency, nowadays even more. And the servers are going to need much less cooling and power supply, both of which can also be done in smarter ways. And we could even save half the utility losses by using fuel cell trigeneration, cheaper than the uninterruptible power supply it replaces. Now, multiply these savings from downstream to upstream, and you get at least 2 orders of magnitude energy savings, possibly 3. In the actual project for which we made this diagram, the client rejected most of our recommendations, so we were only able to treble efficiency at the same capex. But our design partner, EDS, said that had our recommendations that they agreed with, which was practically all of them, been adopted, we would have saved about 95% of the energy and half the capex. And now I think we could do even better than that. Vehicles can use the same design logic. Automobiles' propulsion system or powertrain loses 4/5 of the fuel energy before it can get to the wheels. But our savings should start downstream at the wheels. Here's why. You see, just 1/5 of a modern car's fuel energy reaches the wheels and moves the car. And of that so-called tractive load, nearly half heats the air that the car pushes aside, most of the rest heats the tires and road, and only the last 6% of the fuel energy accelerates the car and then heats the brakes when you stop. Oh, but it gets worse because 19/20ths of the mass you're accelerating is the heavy steel car. So just 1/20th of that 6%, or about 0.3% of the fuel energy, ultimately moves the driver. Not very gratifying after 1 1/3 centuries of devoted engineering effort and all the skill and risk and ingenuity that the petroleum industry puts into recovering the fuel. The rotted remains of primeval swamp goo and dinosaur poop. Anyway, both acceleration and rolling resistance in the bar chart there depend on mass, and thus mass causes most of the tractive load. So, reducing losses in the powertrain, where most automakers focus, is harder than reducing tractive load, because so much has been done on it already, and it's also much less rewarding because saving 1 unit of energy in the powertrain saves 1 unit of fuel in the tank, but saving 1 unit of energy at the wheels avoids 3 or 4 more units lost in getting that energy to the wheels, and that leverages, therefore, 4 or 5 total units of energy saved at the tank. So we should first reduce the tractive load, then improve the powertrain, but then the powertrain shrinks for the same acceleration, saving even more mass, and also saving capital cost to help pay for the lightweighting. You've heard this story before, right, in the other sectors. So we've been playing with this for several decades. There was a brilliant engineer at the Lockheed Martin Skunk Works who did a 95% carbon fiber tactical fighter airframe, 1/3 lighter, 2/3 cheaper. And when that activated the Joint Strike Fighter community's immune system, I hired him to do the same for cars, and we came up with this ultralight carbon fiber electrified hypercar 22 years ago, 4 to 6-fold more efficient, and a 2-year retail payback at $50,000 a year against U.S. petrol prices. In 2007, Toyota designed this 70% lighter so-called 1X carbon fiber plug-in hybrid. In 2013, this profitable quadrupled efficiency carbon fiber electric car came to market. I've told you about that already, the BMW i3. And even aluminum fleet vans like this plug-in hybrid we developed and road tested, 13 years ago, could save 1/5 of U.S. light-duty vehicle fuel profitably with no subsidy. And then carbon fiber autos could save more oil than Saudi Arabia lifts, and yet with radically simplified manufacturing can be made at normal cost. How do we know? Well, BMW did it. You've heard that story earlier today. Here's the policy lesson. Permit me a little eye chart here. I'm going to plot autos' marginal sticker price on the vertical axis against their fuel efficiency, forgive the barbaric units, on the horizontal axis, but I didn't want to get into confusion between US and imperial gallons. This is US. And that sort of plot gives you these kinds of classic supply curves from the US National Research Council of the National Academies of Science. And that's from 2001 and 2015, and it's for both cars and light trucks. And their 2015 updates caught up with previously rejected independent analyses. But all of these forecasts were embarrassingly overtaken by actual market platforms, like for example, Honda's VX, Toyota's Prius hybrid, BMW's i3 electric vehicle, also by a major automaker's aluminum and petrol virtual design they did with RMI, by Porsche Engineering's high-strength steel virtual design, RMI's 2004 base vehicles computed from our Revolution SUV design you saw yielded typical light truck and car versions like these. And then here's an RMI spin-off's road-tested aluminum commercial fleet van you saw a minute ago. So these are 15 empirical data points showing that traditional component-based analysis misses the entire right-hand two-thirds of the design space. That is, when you analyze efficiency by the part, not by the car, efficiency looks several-fold too small and too costly. But integrative whole vehicle design can at least treble predicted fuel savings at a lower cost. And this makes efficiency standards far more conservative than we thought, electrification a lot cheaper and faster than we thought. Much the same is true with heavy vehicles. I mentioned in my earlier talk, very briefly, a lattice and membrane way of making, say, aeronautic structures. These are small molded engineering plastic cells that are assembled by swarms of programmed robots or grad students, whichever are cheaper, and then you wrap a tough polymeric membrane over them. And NASA tested last year a 4.3 meter long test structure that's 59 times less dense than a typical aircraft wing. So it's got the strength and toughness of bulk elastomers, but the gossamer density of aerogel. And without movable flight surfaces, the whole shape adjusts passively and continuously to real-time flight conditions like a bird's wing. So you can make an airplane any shape this way with revolutionary prospects for lightweighting, aerodynamics, and cost reduction. This has been prototyped as a car for Toyota, as an airplane for Airbus. It could make a vacuum balloon using no helium that is light enough when evacuated to be buoyant in air, but strong enough not to crush. And a big one could lift 24 times the payload of a jumbo jet. Now, these lattice structures are made of common engineering plastics like ABS, but it could perform an order of magnitude better with carbon fiber, or 2 orders of magnitude with carbon nanotubes. And one inventor thinks that with such structures and great aerodynamics like the little business jet I showed you with 8x efficiency, and photovoltaics all over the top and bottom, because there's as much light from below as above when you're aloft, and about 4-fold better batteries, a solar electric airliner could fly and take payload intercontinentally. We'll see. That's pretty adventurous, but it may be possible. Now, such magic requires, as Bacon said, some new methods. And let me give you 3 of them. First of all, organize designers differently. Our hypercar SUV's basic design didn't use 1,000+ engineers as usual. It used 7, all around the same table and collectively responsible for dauntingly ambitious whole vehicle requirements that the industry had no idea how to meet. But each engineer was also responsible for one major vehicle system or function. And our trick was, for those systems or functions, we deliberately wrote no requirements, because I didn't want him to make his problem into her problem. We wanted to make the whole team design a highly integrated vehicle together. 2 of the engineers were not comfortable without their very own requirements, so we replaced them in the first week or 2, and then it went fine. And Toyota asked how we did it, and we told them, and out came their 70% lighter 1X that you saw earlier. Second, to make the car half to 2/3 lighter, you must go repeatedly round the design spiral or design cycle. First, you make the auto as light and slippery as you can first think of to cut its tractive load by at least half, and that permits smaller and more advanced powertrain and smaller, lighter chassis components, like you need less suspension to support it and less brakes to stop it. This leaves more packaging space for comfort and more crush space for safety, which is good because you're on the road with heavy things. But then you keep going around the spiral, and with each step, you make the components smaller as their structural loads shrink, because the less weight you have, the less weight you need. And then a lot of big parts start to disappear, because a good series hybrid, which you rapidly get to in this approach, can eliminate, let's see, transmission, clutch, flywheel, drive shaft, universal joints, axles, differential, starter, alternator. It's 9 things that go away, and each of them saves even more mass, and then you go around the spiral some more. So at first, the special materials and powertrain and design may raise your manufacturing costs, but after more mass decompounding like this, you need so little carbon fiber and so little powertrain and manufacturing the advanced composite structures can get so much simpler, as we saw with BMW, that those 2 savings pay for the carbon fiber, making the ultralighting roughly free, just as BMW proved. Thirdly, such novel design processes flow from revolutionary design mentality. Dave Taggart learned at the Skunk Works to design in the future, not in the past. So when the Soviets shot down Francis Gary Powers' U-2 spy plane in 1960, the founding genius of the Skunk Works, Skelly Johnson, did not say, I'm going to design a slightly better U-2. He said, in paraphrase, I want to own the skies for decades, so we'll design a Blackbird. I don't know how, but we'll figure out. They did. It took about 13 months. Because Johnson understood that such an airplane was impossible within the conventional design context. He knew that design is like an elastic band. If you try to stretch it too far from the conventional design space, you encounter more and more resistance, and eventually it breaks. But if instead you jump to the new design space that you aspire to, you can stretch the elastic band back to fit technologies that aren't ripe yet, and then as they mature, the elastic band relaxes to where you want to be. These examples illustrate the immense potential of integrative design, and I have another 18 hours of examples from my Stanford course, but we won't go there right now. But this is not normally recognized, taught, delivered, expected, or rewarded. Very few executives even know you can do it. And as I observe buildings and factories and vehicles in 70-odd countries in 50 years, I see the same design errors repeated everywhere, naturally, because they're widespread in our textbooks and our classrooms. So I'm hatching a plot for, well, to put it a mite impolitely, the nonviolent overthrow of bad engineering. Teaching disintegrated design, as we now do, condemns our descendants to perpetual retrofit of bad stuff, not a worthy legacy. So to help us be good ancestors, I'm seeking fellow students, teachers, practitioners, supporters to collaborate on making integrative design shift rapidly from rare to common. I would like to help retread the in-practice design professionals and the tradespeople like pipe fitters and sheet metal workers and mechanical contractors who informally design many systems. I want to help improve design software to allow and coach integrative design, and even to allow non-orthogonal pipe layout. What a concept. I want to find iconic CEOs to apply 5 ADA in their firms and spread the word to their peers, much as Jack Welch did with Six Sigma. And I'm eager to test about 20 known scaling vectors, see what works, and start scaling. We now have partners in India, Australia, and Sweden who want to collaborate on pedagogic reform with intensive Teach the Teachers courses that I think can spread very rapidly. And that's actually a scaling model, whereas the linear process of teaching 2 classes of wonderful Stanford students a year is obviously not a scaling model. So I hope these examples will encourage you to rethink why global end-use efficiency is only about 1/9 what it could be, how better design and beginner's mind can help to close that gap, and how we can scale up to make integrative design as common as grass. And then the global energy transformation can move at the pace and the cost of design and software, not of infrastructure, and can be not constrained by the inertia of incumbents, but sped by the ambition of insurgents, like many of you. So go forth, be fruitful, and subtract. And thank you all for your good work and your kind attention. Let's see if I said anything controversial.